Welcome to the Selmo Academy tutorial video. In this video we will show the application of the drilling device demo from modeling in Selmo Studio and implementation in a target system to commissioning with the HMI. This model is a simple drilling device to clamp and drill a workpiece. Modeled with the Selmo Studio, target system TwinCat 3, and Boris simulation system. In the Project Explorer, we see the structure of our project. The plant represents the whole system and contains global signals and parameters. To the plant, we add a hardware zone. This defines a sub-area of a larger machine. To create the whole framework for the process model, we need a sequence. The sequence is the heart of our project. This is where the process is modeled. Starting in the logic layer, we create a step chain in a graphical interface with predefined building blocks. We call these building block steps. In relation to our drilling machine, we now model the process which the machine should execute, from pressing the start button to drilling the workpiece. This step chain is the base for our process model. In this simple process, we only need normal steps and a timer step, in which we define the drilling time. But there are also other building blocks, such as a decision, which allows me to decide between two or more paths. A jump, a repeater, and the cross-sequence function, which allows the interconnection of several sequences. Simple but also complex processes can be built very clearly with this method. In the assembly layer, there is a library of many assemblies which we can use for modeling. These contain either complex functions, such as axis drivers, PID controllers, or other mathematical calculations. They also simply serve the purpose of making the modeling of components like buttons, cylinders, or valves even faster and easier. Our model has a start button, two double-acting cylinders, and a motor for the drill. It is also possible to create your own drivers using the Selmo template. If you use these modules, all the required signals and parameters are automatically added to the process model. This brings enormous performance to the modeling of processes. Once all the required components of the machine have been added, we define the states of our individual signals for the respective steps. In the system layer, we mesh our step chain from the logic layer with the signals from our assemblies. On the left, the steps are listed in the modeled sequence, and at the top, the zones inserted by our assemblies. These zones represent the in and outputs of the machine. The zone in is an input signal and is shown in green. The zone in out is colored blue. It switches an output and expects a feedback in the same turn. The zone out shown in red represents a pure output. In the bit control, we set the states of the single steps with the operands 0, I, and S. A 0 stands for no action. An I stands for interlock check. This means the signal is monitored and must be in this state at this time. And an S stands for sequence check. If you set this, an output is set, or the step is paused until the input signal appears. In the manual cross-interlock check layer, we set cross-interlocks for manual operation. For example, we want to prevent drilling a workpiece that is not clamped. All you have to do is set a few hooks, and the generator does the rest. The hooks are used to define the signals that are queried and must be active for the execution of the respective manual function. Safe operation of the system is ensured. In the target system area, we select the target system for which we want to generate the PLC code. Every PLC XML open-capable controller is supported. In this case, we select Beckhoff TwinCat 3. The PLC code has been generated with all information of the process model and is freely viewable. It is exported as XML file and implemented into the controller. In the target system backhof, we will now import the generated PLC code as an XML file. The same project structure as in Selmo Studio can be found in the target system. To control the drilling device, we have to define the variables for the Boris model in a global variable list. Through these variables, the controller communicates with the virtual model of the machine. In the sequence folder, an input mapping as well as an output mapping has been generated. Here we connect now the zones of our process model with the variables we have just defined. In the input mapping the inputs, and in the output mapping the outputs. That's all we have to do in the target system before we can put the system into operation. Not a single line of code was written by hand. The entire HMI is created from the Selmo process model. It provides all the functions which are needed to control a machine. By activating the automatic mode, the process model can be started by pressing the Start button. The current state, as well as every deviation, is displayed in the HMI. Another visual feature is the visualization of the step chain in the HMI. Here you can visually follow the current step of the process. For large and complex processes, this is very advantageous. For predictive maintenance of a machine and to detect deviations, we have installed a step time monitoring. Here you have the possibility to teach the times for each individual step by using the teach mode and to monitor for any deviations. In the next video we show for advanced Selmo Studio user, the demo model indexed line.